Good afternoon, everybody, and welcome to our chemical reaction hazards. Sort of 10 common questions we get about chemical reaction hazards. That's going to be the theme of our webinar today. I'm just going to hold on for a few minutes. For those that are going to join, we're just a little early at the moment. So I'll talk again in a few minutes. Hey, good afternoon, everybody. It's just after 3 o'clock, so we'll give this a start on today's webinar. Kind of all around the theme of chemical reaction hazards, chemical process evaluation. And it's going to be a little bit of a different kind of format today. We're going to go through some of the sort of common questions that me and my staff get from clients, inquiries, some of our colleagues internally, or even sort of family and friends asking, what are you doing at work? So we'll try and run through some of those sort of normal questions, kind of answers we would go to. So let's make a start. So a bit of an overview of today. We'll start with some introductions. So my name is Dr. Ollie Armstrong. I'm the laboratory manager here at Sigma-HSE for the Chemical Process Evaluation Laboratory. I've also got my colleague on the line, Luke, if you want to say hello.
Name's Luke Buckshout. I work in the CRH Lower Volley, Chemical Process Evaluation Technician.
So we will also go through a bit of a wider picture of Sigma-HSE, what we do and what we can offer, not just on the chemical reaction hazard front, but a wider sort of process safety offering. And then the bulk of the webinar will be on, like I say, these chemical reaction hazards. What are the kind of common questions we're fielding around this kind of study and work we're doing. And then we'll kind of close up with the webinar with a bit of a summary. So like it says at the bottom there, we will be back and forth between myself and Luke, sort of asking the questions, some answers, quite informal back and forth. If you guys do have any questions that crop up through the webinar as well, we will try and maybe get to some of those, or any that we don't get to, we will definitely reply to you via email or something after the webinar. So we would invite any questions you've got as we go through. So like I say, the objectives, hopefully from this kind of discussion, you will have a better understanding of chemical reaction hazards, chemical process evaluation, how we kind of distinguish between those two, although we may use them interchangeably at times. Why the understanding of these hazards in regards to your own process it is very important for process integrity and safety. The kind of laboratory tests and methods that are available to assess any of your chemical reaction hazards not just our own, but other alternatives as well. And of course, there are no wrong questions. So Sigma-HSE, we started out in Winchester in the UK. That's where me and Luke are speaking to you from now. We've also got offices in India and in the USA. So we've got our main laboratory here in Winchester in the UK, which has our industrial explosion hazards lab, which is kind of combustible dust testing, gas and vapors, flammability, electrostatics and the like. And then we've also got our chemical process evaluation lab, which myself and Luke are part of. And then we've also got a lab set up in India, which is more focused on the combustible dust testing at the moment. So the technical offices that we have in India and the US also facilitate the sort of consultancy services that Sigma-HSE offers. So this kind of global base allows us to bring together our experts from across those continents to provide our clients with environment, health and safety services, and sort of analysis of our testing data, consulting assessments of processes and how these kind of tie together. So we undertake our laboratory testing, which we'll be talking about quite a bit today, in our UK labs to ISO, BSI and ASTM standards. More relevant to the chemical reaction hazards testing, we are normally using ASTM standards. There's a bit of a lack of equivalent ISO standards available. So we've also got ISO 17025 accreditation for our some of our combustible dust testing offering in the UK, and we are we're working on expanding that to some of our chemical reaction hazard tests at the moment. It's kind of in process. So this is kind of our laboratory offering here in the UK. Of course, at the top, this is what we're talking about today, is the chemical reaction hazard testing. Thermal stability testing can kind of tie between chemical reaction hazard and then other sort of more bulk storage type assessments for looking at, like I say, bulk storage systems rather than the stability of mixtures themselves. And then there, the powder or dust fire and explosion properties, severity, sensitivity, dust combustibility, gas and vapor properties, also flammability limits. We've got a really nice picture there of a upper explosible limit test of a vapor system with a nice bright orange flame. And we also do some electrostatic properties testing to sort of tie into primarily the powder and dust testing as well. And then, of course, like I say, we have our consultancy wing that can provide quite a wide array of offerings to do with process safety, so training, different kind of assessments depending on the specifics of your plan or requirements. Like I say, training workshops, trying to outskill. So we're starting with question number one. Yeah, go ahead, Luke.
Question one. So quite a common question. What is a chemical process evaluation? So I'll let Ollie answer this one actually.
So this kind of goes into why we're looking at chemical reaction hazards and how it ties back to chemical process evaluation. So many desired reactions or syntheses will have an inherent risk of exothermic decompositions. So that's not just looking at what happens when you do your desired reaction, what happens if for some reason things may run out of control or a reactor is subjected to a sustained fire and heated up externally. your material might start to decompose itself and generate its own heat in that case. So the kind of, for us, the difference between chemical process evaluation and chemical reaction hazards may look specifically at testing one parameter. What happens if I heat this mixture up to 400 degrees? The chemical process evaluation is more of a tie-in of a suite or package of testing, which is looking at various eventualities and the desired process itself, looking at each of these parameters in a round to assess the process as a whole. So, like I say, chemical reaction hazard may just be data itself, whereas chemical process evaluation feeds from the data, but informs part of your assessment, and then integration into how you're actually going to operate your process and put safety controls in place. So the reason you may need controls on your process, so heat generation, gas generation, and vapor generation are all kind of key risks to your process integrity. Also, that needs to feed into your assessment or evaluation are any potential process deviations. So this really requires a detailed knowledge of A, the chemistry you're actually going to be performing, and B, also the configuration of your plant, the servicing, all the kind of valves and pipes and things like that that may have an impact on how your process could go wrong should the worst happen. So this kind of full view of any potential abnormalities and this in-depth knowledge is the most robust way to develop a basis of safety for your desired reaction or process. I'll click on. So we've got two sort of basic flow charts here about that kind of visualize where our testing, chemical reaction hazard testing, may fit into a chemical process evaluation journey or R&D scale-up journey. So the top left is very much more from the focus of our clients, and I presume most of the people online today. Going from left to right, the kind of key milestones in a new process project development timeline. So early on in the process, we're looking very much at kind of literature and calculation methods, what may be unsafe to handle or to react in a certain way to sort of screen out the most hazardous pathways. Moving on to sort of identified routes, you may start then looking at thermal screening techniques, which we'll talk about a bit further on as well. Some of this testing should help inform which route you then want to choose to go for and the optimization of this, which leans heavily on reaction calorimetry testing as well. And it's about this point you start doing some of your assessment. Like I say, if this is for a new process, you may not know what your plant and services looks like exactly at this time if you're setting up a new reactor to do this process. So the kind of minor hazard assessments need to look at feasibility of the reaction itself. And then when you're looking to pilot scale, that's where you start thinking more about the configuration of the whole plant and what really could go wrong and what potential impacts this might have. So like I say, at the later stages there, we also need to look at adiabatic calorimetry, which we'll again talk about later on, and this must inform your basis of safety for your process. And then the chart on the bottom right is more from our point of view, the kind of tests we may offer at different stages through. So from top to bottom, we're looking at sort of thermal screening methods, our differential scanning calorimeter, carrier's tube. These are good for kind of highlighting any potential decompositions that may cause you an issue. But when you get closer and closer to bulk production scale, then we should really be looking at adiabatic techniques if there is any potential risk. Obviously, it depends on each individual's kind of risk appetite, but the adiabatic methods are much more give much more confidence in the results about where decomposition limits may be.
So moving on then, we have question 2. Why is it important to study intended reactions or normal operations?
So as we touched on a little bit before, many of your desired reactions themselves, not just decompositions and unwanted reactions, but the desired reaction will themselves have byproducts of heat and potentially gas. Or they may not be byproducts, they may be the desired products. So any potential exothermic reactions that you want to perform, they need to be quantified. You need to know how much kind of heat output you will be getting from the reaction should and when you take it to large scale on plant. So that will allow you then to specify your process and plant adequately for the reaction that you want to carry out, and to implement any controls that are going to be required to run this process safely. So just as a bit of an example, this would typically be understood as a decomposition reaction, but say for the purposes of this that we wanted to produce water and oxygen on the right hand side, and we only had some hydrogen peroxide, our reactants, on the left hand side. We are starting with our reagents, our reactants, our peroxide. We're heating it up through a transition state, and then the products, the sum of the enthalpy of the products gives us a negative enthalpy change, which results in an overall exothermic reaction. So the reaction moving from reactants to products is giving out heat. Not only this, it is also generating oxygen gas. So we talked about before, it's not heat output that we only need to manage, it is also any pressure generation. So producing a gas in a confined space is going to increase the pressure. So just as a little example, for the 2 moles of reactants of hydrogen peroxide we have at the start, that is only going to occupy 47 mil volume. But our product with 2 moles of water and 1 mole of oxygen are going to occupy a much larger volume, primarily from the oxygen gas. So quickly running through this as well, this is also why it's important to look at your desired reaction, not just decompositions. So we've got a bit of a demonstration here where kind of region 1, the normal process at the bottom left, shows we've got our batch reaction, all our reagents are loaded in, and then we heat up the system to commence the reaction. Dotted line would then show what we would want the process to normally operate as. Where we see the solid line deviate from the dotted line, this kind of grey region is indicative of the reactor cooling failing, and your reaction proceeding exothermically, giving out heat and raising the temperature of the reaction mass itself. And this gives us an adiabatic temperature rise from your TP, your process temperature, to MTSR, which is the maximum temperature of your synthetic reaction. So that is your desired reaction. What is the maximum temperature that system will achieve if you allow it to just heat up itself without removing any heat from it. Now, to demonstrate in this plot, the uncooled desired reaction has then gone on to trigger a secondary decomposition reaction, which is in the darker grey in the top right. So this decomposition reaction then itself starts to give out or decompose exothermally, which has a secondary adiabatic temperature rise, which is this whole system is in effect a runaway reaction because it is now completely out of control. This again kind of links to differences of scale and how it ties into your project development timeline. You may be running synthesis tests early on in sort of typical laboratory glassware, small scale. Now, when you have a small scale system, your surface area is relatively large and you can lose heat much more readily to the environment. When you take to bulk scale, your relative surface area is much decreased, and therefore it's not just about heat losses to the environment being reduced, but if your cooling capacity is a cooling jacket on the outside of the vessel, you've got a lower surface area and your cooling capacity is therefore much lower for a large scale bulk system. And if this occurs, this plot kind of shows a reaction giving out heat externally. The green dotted line shows the cooling capacity of the cooling jacket on the reactor, and the heat generated from the system outstrips this cooling capacity, and this in effect triggers a thermal runaway. The reaction is now out of control. It's given out so much heat that the cooling system can't remove it. So it's not just a case that your cooling system may fail, as in it shuts off, but it may not have enough capacity to remove the heat required. This all kind of links into, I mean, a simple way of reviewing a reaction based on reaction calorimetry and thermal stability studies is to define a criticality class. So these are taken from Francis Stoessel, and they kind of move from number 1 to number 5 in the greatest risk. Criticality class 1 is very low risk. Your desired reaction is not going to get you to a temperature at which your decomposition may occur, and it is also below even the boiling point of your solvent at the MTT, so you're not even going to get vapor generation at this point, or extreme vapor generation. Through to criticality class 5 on the right, your MTSR, so that is your uncooled desired reaction, takes you all the way up past your decomposition onset, and then your boiling point, for example, of your solvent is then even higher above that. So you're not going to have any tempering of the reaction by boiling off solvent and removing heat that way. It is just your desired reaction is going to go straight into a decomposition reaction and run away at that point. So question number 3, I'll ask you this one, Luke, please.
Sure.
What are some common worst case scenarios?
So yeah, I mean, you touched on it in the previous couple slides, but improper assessment of scale-up differences is quite a common reason for experiencing a worst case scenario. Obviously, the heating and cooling requirements can vary exponentially with batch scale, but also if you don't think too hard about it and you design your reactor around normal operation, you're not considering a worst case, which can actually be quite catastrophic. You obviously have your system failure, so that could be, failure of vacuum, failure of stirring, which results in accumulation. But then you also have things like operator failure or process failure, which, if you go on to the next slide, we can see some causes of failure. Mischarging of reactants being the largest one. This can be too much of one reagent too quickly, or it can just be the completely wrong reagent. If you're in a company that deals with multiple chemical processes, it's not unheard of. And this sort of thing can cause unwanted, unknown reactions that can be extremely violent. Even for chemicals that aren't used in the chemical process, cleaning agents, there's been cases where mischarging large volumes of, I think it was 2 acid-base cleaning agents, nitric acid and the other containing isopropanol, actually resulted in the formation of isopropyl nitrate, which used to be used as a rocket propellant. So very explosive and really quite catastrophic. You can also see lack of thermochemical knowledge, essentially not scaling up properly, not having that data to hand to be able to accommodate any adiabatic temperature rise or energy of the reaction with your current control measures. And then we also have the inadequate temperature control, so failure of cooling or overheating, which can then lead to the thermal runaway events. Obviously, once this happens, the rate of reaction increases exponentially with temperature, so it's very difficult to stop the reaction before these high temperatures initiate thermal decomposition of the reagents. So go to the next slide. So some of these potential process deviations can only be identified with a detailed knowledge of the chemistry in the plant. Obviously, part of the consultancy arm of Sigma-HSE can help to ascertain those risks, and we can run through this sort of assessments here. We have the HAZOP, computer assisted studies, what if analysis, failure modes and effects analysis, and the checklist and fault tree analysis. Moving on. So question 4, I'll chuck this one back to you, Ollie. Which key parameters are analysed when assessing chemical reaction hazard data?
So we've kind of touched on some of these before in some of the other questions. The key kind of measurements we take from our thermal stability, reaction calorimetry, and adiabatic testing. We're measuring temperature and pressure. So temperature primarily can relate to we're needing to test the systems as close to how they will be performed on plant. So what is the temperature set point of your reaction? There's no point us testing a system at 0 degrees when it's going to be operated at 50 degrees on plant. And then also temperature is very crucial for any decomposition onset temperature points. There's a lot of stock put in these onsets for assessments. Adiabatic temperature rises that we discussed a little bit before. Every reaction is allowed to proceed adiabatically and heat up its own mass. What is the temperature? What is the adiabatic temperature rise going to be? And we can also do some assessments sort of isothermally. So we may do an isothermal assessment for reaction calorimetry, but also for assessing thermal stability. We may have a need for heating up a material to a certain temperature and holding it for 12 hours, for example, to assess whether it's going to start to trigger a decomposition over that sort of time frame. And then also discussed before, pressure. That is a key one for us to measure in situ of our tests. For example, in the analysis of our kind of results would be any kind of permanent gas that's generated. This can either be a total volume, how much gas is generated for a reaction, or for thermal stability assessments, for example, if you have a decomposition, what is the volume per mass of material? the volume of gas produced rather per mass of material, starting material, product, what have you. So pressure as well also relates to a lot of chemical reactions are produced on plant within primarily confined systems. So this kind of pressure or potential for pressure buildup really needs to be assessed properly and with full knowledge and data. So from these two parameters, temperature and pressure, we can also look at measuring and assessing enthalpy, either your reaction enthalpy of the reaction you want to occur. This can help with kind of R&D optimization steps. If you perform your reaction as you are intending to, and you match up the measured enthalpy against what you thought it might be from your literature calculations, and it doesn't really match, then maybe you're getting a low yield in that reaction, and you should look at, for example, your temperature set point or feed rates or what have you, or mixing agitation needs. So that's more about kind of your desired reaction, but we can also look at enthalpy for decompositions. If a material is heated to a point where it starts to decompose at the onset, how much energy is that decomposition going to give out as well? And then finally at this point, kind of rate. So that can be temperature rise rates, pressure rise rates, reaction rates, kinetics, bringing it back more to the chemistry, and also sort of gas flow as well, which is another rate. So a lot of this is absolutely critical for assessing sort of vent sizing requirements for reactors. But also if you are producing a gas, whether it be from your desired reaction or unintended reaction, what is the nature of that gas? Is it toxic? Has it got some other kind of health hazard to it? Are you going to need to scrub that gas? What kind of capacity do you need to be able to do that safely and properly? So yeah, just to hammer home again, really, that the pressure for these kind of systems really is a key hazard. It's easy to assume that the temperature increasing exothermic energy is going to be the key thing, but that in itself leads to pressure generation either by vapor production or greater gas generation. So just to summarize, overpressure in a reactor can come from three potential sources. Like I say, gas generation from your normal process. Is it producing a byproduct of a gas? Vapor pressure, you're heating your system up. How much vapor is going to be produced from some evaporation of your solvent? And then finally, just to wrap it all together, if you trigger a decomposition or a secondary reaction, this kind of effect of generating gas or vapor pressure is only going to be increased over and over again. So Luke, if you want to lead us through a little bit here, we've got question number 5, which methods are used to screen for thermal stability?
Yeah, so at Sigma, the two methods we have to screen for thermal stability are the differential scanning calorimeter and the Carius tube. There are others available. I believe Ollie will be talking through them in a later question. But we'll start off here with the differential scanning calorimeter. So the DSV on a typical program, it will heat the sample, normally about 1 to 10 milligrams, 5 milligrams is normal. It will heat the sample to 400 degrees, typically at a rate of 5 degrees a minute. So the test all in all only takes a couple of hours. It's quick, very useful if it's a reaction that's very early on in its development. You don't have much sample. It's the perfect sort of screening test to get an idea of any energetic events, phase transitions, morphological transitions. So yeah, it's quite a handy bit of kit. And if we go on to the next slide, we can see a bit more about how it works. So all these sort of measurements are taken by comparing the high pressure incloy crucibles, one of them with the sample in and one would just be an empty reference cell, hence the differential in differential scanning calorimetry. So because of the really small amount of sample compared to the mass of the actual crucible, the 5 factor is much higher than some other adiabatic tests. So this is, more indicative of potential chemical reaction hazards rather than a absolute quantification of things like enthalpy and exothermic onset temperature. So next we have the Carius tube. The Carius tube takes a bit of a larger sample, about 10 grams, and this allows for more representative samples to be taken, especially if it's a heterogeneous mixture. It's much more feasible to actually get results that are representative. This takes a bit longer, about 12 hours per sample, but it also provides onset temperatures for energetic events, phase transitions. So if we look on the next slide, we can see that the Carius tube works in a similar way. It takes the differential temperature between the oven and the sample. The only difference is really it doesn't actually quantify the enthalpy. However, it does have the benefit of being able to record pressure data. So we can determine permanent gas generation onsets, but also how much gas is generated from the decomposition. So that moves us on to question 6. What other methods are used to obtain chemical reaction hazard data?
So I kind of touched a little bit on some of this before. Sort of early on in an R&D timeline, there may be a lot of emphasis on some literature methods. So enthalpy balances, what do you expect your desired reaction to do? In terms of thermal stability of products, we can look at the oxygen balance, and this may highlight any potential highly energetic decompositions or even explosive properties. So these are just good tools to sort of start informing you on your new process journey early on. Same with the simulations. There's various software such as sort of Cheetah and AKTS and Prove, I think. These simulations will allow you to put in reagents and desired products, and they will in effect do the same kind of thing that you're doing from your literature, or kind of give you an indication of what kind of criticality class you might expect your reaction to be, and any potential thermal stability issues of your products. So these are good to make some kind of decisions about which process pathway you're going to go down, but really the kind of testing data and the different methods available to test are the best way to justify your basis of safety for your new process. So Luke's already discussed the DSC and Carius tube that we have here at Sigma-HSE. We'll talk about some other tests we have available as well later on. But this is really just to highlight there is quite a range of other equipment and test systems out there that will all kind of have their own little niches and applications. So on the screen we've got our thermal screening unit at the top left, which I think we mentioned before. We've got a Calvit C80, an EV Plus, which is a type of ARC system, but that's specifically for testing sort of large battery systems. We've got a VSP2, we've got an RC1, Metler Toledo, and there are others sort of ranging from very small scale, fast throughput to large scale, highly accurate adiabatic systems. So there really is a lot of choice out there for what exactly are the specifics of your process that you need to test. Where are you in your new process timeline? Will kind of dictate what test systems are most appropriate to give you the best data and most appropriate data.
So question 7 then, why do we use adiabatic methods?
So we talked about it a little earlier on, I think, sort of the differences of scale, right? So bulk systems have much lower heat losses because they've got a smaller relative surface area. So adiabatic in definition means a zero heat loss system. So all of the heat within the system is retained within the system. So why is this important for exothermic reactions? These adiabatic methods allow us to measure any heat produced within the system being retained within the system, and it is consumed by increasing the temperature of the mass within the system. So that's where we talk about adiabatic temperature rises, right? Where our reaction mass goes from our temperature set point, the reaction occurs exothermally, heating up completely the reaction mass. There isn't any of that heat being generated that is being lost and spent on heating up the environment around it. Again, the importance of this, differences of scale, bulk or large scale systems can be assumed as relatively close to adiabatic. They are not adiabatic systems because they have an environment around them, but compared to small scale, lab scale, they are vastly closer to an adiabatic system. This kind of also ties into phi factor, which we will sort of analyze and talk about a lot in our chemical reaction hazard reports. So phi factor allows us to kind of account for the differences between different tests that we may perform in the lab, to account for the differences in how they work in effect. So second bullet point there, heat generated in a reaction is consumed in 3 ways again. To raise the temperature of the reaction mass itself, which is what we were saying an adiabatic system will do, only that. Secondly, it will raise the temperature of the reactor itself, the materials of construction that are holding that reaction mass. And then third and finally, any heat losses to the environment. So if we say we have an adiabatic system, we've already removed that factor of heat loss to the environment, but you're still having heat consumed in heating up the vessel walls itself, which is where phi factor comes into it. And it just accounts for that relative additional heat loss for heating up the vessel. So there are various kind of phi factors. Our arc test may be between 1.5 and 3. ARSST VSP2 might be 1.05 to 1.5, for example. Carrier's tube, a screening test, will be 2.5 to 5. Ideally, so a phi factor of a large bulk system will be close to 1. So 1 is the kind of perfect adiabatic system. Which kind of leads us neatly onto some of our adiabatic testing methods. Luke, what is the difference between the ARC and the ARSST?
Yeah, so really the main 2 differences between the ARC and ARSST is that the ARC is a closed system and only deals with sort of batch reactions. So you chuck everything in and then just set the program running. The ARSST is a bit more versatile in that sense, in which it's an open system. It's a test cell within a larger containment vessel, and we can actually analyze reactions. We can do liquid additions for them. as Ollie said, they're both adiabatic calorimeters, and they're both designed to record temperature and pressure data for quite a various chemical reactions. The data from both tests can be used to evaluate the thermal stability, kinetic behavior, but only data from the ARSST should really be used to perform things like vent sizing analysis. And that is due to, like Ollie said, it's much lower 5-factor using a glass cell. Firstly, though, we'll talk about the ARC. So it has a closed cell bomb, as I mentioned before, and we have a few different materials that can be made out of, depending on the chemical compatibility with the sample. So we can have titanium alloy, steel, or Hastelloy. Like Ollie said, slightly larger 5-factor, but still a good test to sort of represent and simulate adiabatic conditions. The arc only has a small headspace, which would just be equal to the volume left over after you add the sample. And the arc only has 2 modes of operation, really. And that's the heat rate search mode, which provides most of the useful data, the adiabatic temperature rise and exothermic onset point, whilst the isothermal testing is a bit more niche if you need to see whether a sample or product will decompose after being left at a certain temperature. So the arc will match the sample temperature it'll match the oven temperature to the sample temperature to try and minimize the heat loss to the environment, and that's how the arc will try and achieve its adiabatic conditions. And now we can move on to the ARSST. Like I mentioned before, the ARSST is slightly more versatile since it can study liquid additions. You can have a syringe in the top, and you can monitor the reaction as soon as it's initiated. It also has the capability for stirring, so it has some capabilities in reaction calorimetry. It uses the glass test cell, which obviously means it has a very low 5-factor, which is just slightly more accurate and more representative of large-scale processes, which is why it's preferred to use the ARSST for things like vent sizing analysis. So we can see it's contained within this 350 ml vessel, and that's just to accommodate any pressure generation. There's a lot of leeway there, but it also means that we can impose a nitrogen pad to investigate and suppress any vapor generation or boiling. So we move on to the next slide.
Okay, so we've talked about it quite a lot already, but we'll look at sort of reaction calorimetry now. So question 9, what functionality does the reaction calorimeter have?
Yeah, so the reaction calorimeter is especially useful for modeling large-scale batch reactions. It has automated dosing capabilities, and it's very representative of the flow dynamics you'll see with large stirrers in these sort of pilot scale and above processes. So it has 2 heat quantification modes. We have heat flow calorimetry and the possibility for power compensated calorimetry. And we have quite a wide working temperature range of -60 to 220 degrees Celsius. So this helps us to design a bespoke testing regime to match the desired reaction for study. So we go on to the next slide. You can see that's a glass reactor vessel, and we actually have that surrounded by a water jacket, which is in turn surrounded by a vacuum, so that the only heat transfer between the water jacket and the reactor vessel can occur. This increases the accuracy of the measurement by decreasing the 5-factor, which we've talked about before. So the heat flow calorimetry closely monitors the temperature difference between the jacket and the reactor, which is then converted into heat flow by means of a calibration factor. So this method takes a little longer because we have to calibrate before and after the reaction, since the thermal conductivity of the solution will change as products are formed. We then have the power compensated calorimetry, where we typically set the cooling jacket to about 5 or 20 degrees below the desired process temperature, and then the process temperature is maintained by an electrical heater, which has a large surface area. As the heat load of the reaction changes, this heater can be controlled to maintain those isothermal conditions. So essentially, the inverse power supplied to the heater will equal the heat generated or absorbed by the reacting system in the vessel. Now, this will typically be used sort of near the end of a sort of process life cycle, in which we'll need quite a large amount of samples to be able to run these reactions. So this is, like I said, good for modeling, pilot and above scale. So yeah, we also have the ability to quantify the reaction enthalpy in this method. We can quantify accumulation. We can use a pH probe to monitor the pH of the reaction. We also have the capabilities to measure gas flow, and if necessary, we can track product formation with the use of an IR probe. So really versatile bit of equipment. So that moves us on to the last question. I'll let Ollie take this one. It's, what does a useful chemical process evaluation look like?
Okay, so for us, obviously, as a process safety company, our focus is providing services to make sure that you can conduct your processes in a safe manner with a good basis of safety. But there are also other reasons you would want to run an sort of useful and adequate chemical process evaluation. So linking it into your project timelines closely will help you progress through various stage gates as you progress, keeping everything on track. As we've discussed a little bit with sort of reaction calorimetry, the actual reaction synthesis itself can or may be optimized from some of this data. But further than that, I also think that the outputs in terms of heat evolved, how is the process and the plant going to need to be designed and set up to run this process? You're going to need to make sure that you have sufficient cooling capacity or scrubbing capacity or venting, but you will, having had the data and the knowledge, you'll know what you need to expect, and you won't be oversizing for these kind of things. So there is potential cost saving there at that point, that everything has been designed adequately but not over the top. Of course, it is useful in providing a robust basis of safety, pinned and based on data and measurables. Like I say, there's been some potential cost savings there. And the robustness is based on the utilization application of chemical reaction hazard data. And that bit kind of links back to what Luke was talking about earlier, potential causes of these kind of runaway reactions, lack of thermochemical knowledge. So not just taking the data for what it is to plug into your assessment, but being cognizant of what it actually means, what are your byproducts that you're producing, and so on, and how to handle that. So this is a rough kind of assessment strategy. It's taken from a HSE in the UK regulatory body assessment strategy for performing a chemical process safely. So again, it's just another way of visualizing what we've already been through really here, starting out early on, maybe by literature or simulation or testing. Is your mixture or compound potentially explosive? Get it tested. If it comes back explosive, then seriously think about potentially changing your route or your process. If it isn't, we can go to the next stage gate, start looking at thermal stability. So our sort of screening test that we talked about, DSC carriage tube, run these tests and see if any kind of decomposition events of interest may occur. If they don't, then fantastic, you can just move on to the next stage. If they do, what kind of potential mitigations can you put in place? So is the maximum safe operating temperature above the boiling point or max heat supply temp? In that case, you know, you haven't got an inherent risk of a runaway reaction occurring. Then we come to reaction exotherms, such as reaction calorimetry. If your reaction proceeds uncontrolled, are you going to generate a load of vapor from boiling your solvent? Are you going to reach a decomposition onset? What kind of controls can you put in place? How can you optimize your process so the risk of that happening is much reduced? Moving down to gas evolution. So again, this is more coming up to your pilot and plant scale. Can the maximum rate, there's the word rate that we talked about before, what the pressure generation rate, are you able to handle it either by venting? Can you literally allow it to leave the vessel fast enough? And then if you do need to scrub it, what kind of capacity do you need? And what kind of processes you need to put in place to do that safely. And then right at the bottom, again, consider process abnormalities. Have you considered anything that may go wrong with your plant to trigger one of these other potential events? It's always good to really come back to that at the bottom, just in case anything has been missed on the first time through. And like I say, if you've done your assessment early doors, you may not know exactly what your plant looks like. So go through all of these stages, have your plant design P&IDs set up, you know what it's going to look like. Think again, what kind of process abnormalities may occur now that has been sort of established. When you've gone through the loop a couple times, 3 times, you can sign off your assessment. But of course, any kind of changes to the process that has been assessed must, of course, then feed back into this loop again. If you're changing your solvent quantity, if you're changing your raw material feed quality, if you're putting it into a different reactor system, all these kind of things. These little changes, they may feel like little changes, but they do need to be part of your change management assessment, and to go through these stages again is very useful. So that kind of brings us to the end here of our 10 kind of common questions for chemical reaction hazards. So at the outset, we kind of went through why we use chemical process evaluation and chemical reaction hazards, the obvious similarities between the two, but where we pin the differences. Why testing data is important to carrying out these process safety assessments and giving a really solid underpinning. And then also the different kind of methods. We've talked about different testing methods, but also different process safety and risk assessments, like the HACCPs, FMEAs, the different kind of ways available of going through this process. So just to highlight again, we've got our kind of consultancy offering and our process safety testing with different options there. We've got some of our contact details at the bottom there. I can see most of the attendees have been on the call throughout the time, so thank you very much for your time on this webinar today. Like I said at the outset, any kind of questions or comments, or if you want to get in touch about anything, we'll always welcome that, and we'll get back to you as soon as we can. So all I can say is thank you very much again for joining us today, and thank you, Luke.
Yeah, thank you.
Cheers.